All right, let me start over, because this is being recorded, of course. All right, today we're going to talk about Chapter 7, how that's aqueous solution. So, of course, we're going to talk about water. Water is a truly remarkable substance. You often hear about life on other planets or whatever, and the first thing people always talk about is whether or not there's water. Well, there's a reason for that. The biological processes that we understand are virtually impossible without water. It's an amazing substance. We're going to start off talking about bonding, covalent bonds, and then we'll move into solutions. Hello. The bonding that we talked about was covalent, where we have a pair of electrons shared between two atoms, and ionic. In an ionic bond, you totally transfer an electron from one atom to the other, and again in a covalent, you share them. In reality, bonding is a whole spectrum between these two limits. Perfect sharing and no sharing at all. To make a covalent bond, we said we take an atom. In this case, we have one unshared electron. We're going to move another atom with an unshared electron up next to it so that we can share this pair and therefore give each atom in the compound a full octet of electrons. Now that is perfect sharing. We have two identical atoms and they're sharing this pair of electrons. When we go to represent this, we said we could also just stick this in as a dash, and remember that whenever we see the dash, that represents two electrons shared. But the sharing is not always perfect. In fact, it almost never is. Let's consider two cases. Molecular hydrogen. That exists as H2. And this is hydrogen fluoride. One hydrogen, one fluorine. Again, they're both molecular compounds with covalent bonds. If we want to know about the electron distribution between these atoms, we can run a computer program and calculate what's called an electrostatic potential map. The electrostatic potential map basically describes the electrons surrounding the atoms. For hydrogen, it looks something like this, kind of like a slightly, well, a little bit of an oval-shaped egg, whatever. But this is colored uniformly green. And that indicates that the electron distribution between these two nuclei is really uniform. Now that's not unexpected because they are identical and they are sharing perfectly. For hydrogen fluoride, however, we get something slightly different. For hydrogen fluoride, we get a really pretty little Easter egg in our electrostatic potential map. Now, in a potential map, blue is used to indicate the absence of electrons. So you can read that as a positive charge. When you have a red color, that means you have lots of extra electrons down in here. What this tells us is that the electrons in this covalent bond are shifted so that they're pulled away from the hydrogen towards the fluorine. Now the reason for this is something called electronegativity. It's an inherent property of an atom, and basically it's the ability of the atom to attract electrons to itself. The most electronegative element is right here, that's fluorine. Least electronegative is down here. This is francium, actually. And there's a gradient that kind of goes across the table this way and up every group. It's an approximate thing. These little numbers under here represent the electronegativities for given atoms. Now, if you look at hydrogen fluoride in terms of electronegativity, hydrogen is 2.1 on that scale, and the fluorine is 4. That means that the fluorine is going to suck the electrons towards itself, and we're going to get an electrostatic potential that looks like this. By the way, these are on the same scale. So we show these as a little bar like that, but in fact, this is more or less what the electron shell around it really looks like. Now, when we have a distribution such as this, we refer to this as a dipole. We say that HF and this bond in HF has a dipole moment. We show that using an arrow. We cross it at one end. Now, you don't have to actually color it like this, but that looks nice. This means that this end of the covalent bond is positive, and this end is negative. The difference in electronegativity describes how polarized a bond is going to be. Any questions on the concept? All right, let's look at something that's near and dear to us, and that's water. Start off on your little sheet there and draw me the Lewis structure for water. Remember how to do that. We look in the periodic table, we see oxygen is there in group 6, so it has 6 electrons. That's going to be 2 pairs of electrons and 2 singles. Oxygen is going to look something like that. Now, hydrogen is in group 1. It has 1 electron. And we're going to form covalent bonds with each of these unpaired electrons. When we do that, we wind up with something like this. Now, if we convert these to line bonds, this is what we get for water. Now, you'll note that I drew these 2 waters more or less at right angles, right? I did that for a reason, as opposed to up and down, because there is something called valence shell electron repulsion theory that describes the shape of covalent molecules. Now, we don't talk about this in 110. In general chemistry, you will. But valence shell electron pair repulsion tells us that this is what water will look like. The whole premise is we have 2 unshared pairs. Go back to this. We have 2 unshared pairs, right? All of these electrons want to get as far away from each other as they can. And the way they can do that is a shape like this, called a tetrahedron. And in this, all of these electron pairs, the ones in bonds and the unshared, are as far apart as possible. If you just look at the water molecule, you go zoop, 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 and you describe it as being bent. All right, so this is what water looks like. Let's look at the electronegativities of hydrogen and oxygen. Hydrogen is about 2-ish. Oxygen is 3.5. Much more electronegative. Now, what that means is that there's a dipole from here up to here, and here to here. So each covalent bond has its own separate little dipole. Each of these bonds is polarized. Now that means that the hydrogens are going to be electron deficient or positive, and the oxygen is going to be negative. We have a dipole moment that looks something like this. This whole end of the molecule is positive, and this whole end is negative. So if we take water and we run our computer program and ask the electrostatic potential map, what we get is something that looks like this. We have a nice blue bottom, that's here. Nice red top, that's here. And our dipole runs like this. It's the fact that water is bent in geometry and that it has this significant dipole that makes it such an amazing solvent. The polar nature of water allows it to dissolve ionic compounds to form solutions, and we remember that's the same thing as a homogeneous mixture. Now let's just take a minute and look at a cute little movie. The movie is going to show a crystal of sodium chloride dissolving in water. It's animated, but looks something like this. What you want to pay attention to is the waters as they come in and as they pluck the sodium and the chlorides off the face of the crystal. There goes the sodium. There goes the chlorine. Another chlorine, another sodium, etc., etc. Very cooperative thing. You see how they all work together? Isn't that neat? Well, there's one subtle thing that I hope you notice that most people don't about how water manages to pluck these ions off of the crystal face. And that is the orientation of the water molecules as they do it. Every time we pull off a chloride anion, the water molecules around it are all oriented with the hydrogens facing inward. That means the big blue spots here are all facing the negative charge. Now why is that important? Because the water with its dipole is able to take this negative charge and spread it out. Nature abhors a single charge of any sort. The more you can distribute it and spread it over space, the more stable it is. Water is the best substance we know for doing this. Same thing for the sodium. You notice the sodium here, always the oxygen ends came in. The negatives interacted with the positives, distributed positive charge, and makes it more stable. Now we can actually calculate this a little more closely. Let's start off just with a sodium ion, which is blue because it's positive. This is the electrostatic potential map, sitting here in the middle, and I'm just going to put 3 waters around it. They're all pointed in with the oxygens, which are negative, pointing inward. I can take my computer and calculate the electrostatic potential map for the whole thingy, and when I do, I get this. And the striking thing here is that this big blue ball that was right here, this is the big blue ball, is totally gone. We've taken this positive charge and distributed it over these 3 water molecules. Actually, if you do this a little bit more, realistically, the sodium cation would be surrounded by 8 waters. If you calculate the whole cluster, you can't see any positive charge left at all. Water is just absolutely amazing in its ability to do this. Any questions? All right, let's work on some terms here. We're going to talk about solubilities, solvents, and solute, just to make sure we know what we're talking about. If a substance dissolves in something, it is soluble in it. Solubility quantitatively can give the maximum amount of the substance that can dissolve under a set of conditions. If we had magnesium carbonate, for example, we're at room temperature, 1 atmosphere pressure, so just like today, sort of. We could dissolve 0.53 grams of magnesium carbonate in a liter of water. That is defined as its solubility, the maximum amount under a given set of conditions. If we had this maximum amount in here, we would say that this solution was saturated. Saturated. We can't get any more in. Again, solvent, the thing that's dissolving, and solute is the thing that is being dissolved. Now, the one thing I told you that was a lie is that solutions can be saturated. Well, they can be, but if you really play tricks and you're really careful, you can actually make a solution that's not only saturated, but has too much of something in it. That's called supersaturated, like supersize. This is a flask containing sodium acetate. Sodium acetate has a defined solubility. But if you put sodium acetate in water and you warm it up, and then let it cool very, very, very slowly, and don't breathe around it, don't touch it, don't wiggle the room, don't do anything, it'll stay here in the liquid phase, in what's called a supersaturated state. Way too much in there. What we're going to do in this little movie is take 1 crystal of sodium acetate, drop it, when it crystallizes, kind of neat to watch. It'll land about there. The second it hits, there it goes. You see crystals start to form instantly as this stuff goes from supersaturated to saturated. And in this case, the entire flask just simply sets solid with all of the sodium acetate. It's this really fun thing to do. Difficult, but it's this fun thing to do. The flask also gets really, really hot when this happens. And this is a kind of neat way for storing something like solar energy. You use solar energy to warm this up so it goes supersaturated. Then when the sun goes down, you give it a little bump, crystallizes out, get all that heat back. It's really kind of a neat cycle. Any questions? All right, when it comes to solubility, there's a rule of thumb, and that is simply like dissolves like. Basically, what we're talking about when we say like is polar molecules dissolve polar molecules, nonpolar dissolve nonpolar. Now, what do we mean by that? Polar molecules will have polarized covalent bonds. like the OH bonds. Those are polar covalent bonds. The nonpolar, the bonds are not very polarized at all, and well, they're just nonpolar. An example, alcohol. The OH in alcohol is just like the OH in water. It's very polar. Therefore, even though this end, the CH3, CH2, is very nonpolar, this is polar enough that it is totally soluble in water in all proportions. The word we use is miscible. So we can take ethanol, the alcohol of consumption, pour it into water, and it dissolves completely because it is polar and the water is polar. If, however, we had something like oil, olive oil. Olive oil is long chains of carbons and hydrogens. These are very nonpolar bonds. Water is very polar, this is very nonpolar. They don't dissolve. They don't dissolve, they sit there as little globules, have to shake it up to make salad dressing. So the simple rule is like dissolves like. We're also going to talk about something called electrolytes and non-electrolytes. Electrolyte is simply a substance that when you dissolve it in water, that solution will now conduct electricity. Water by itself does not conduct electricity. The pure, absolutely pure water does not conduct electricity. But if you have something, if you have an electrolyte dissolved in it, it does. The difference between electrolytes and non-electrolytes basically, or can be measured by this little thingy that we use in lab. It's kind of cute, actually. You may have used this if you took Chemistry 100. You'll use it again in General Chemistry. It's basically a battery, a little bit of electronics, and a couple of LEDs. If you stick this in a solution that's an electrolyte, you will conduct electricity between the two prongs, and your light will glow brightly. If you stick it in a non-electrolyte, it doesn't show up here very well, but this is really dim, kind of blackish, because it's not conducting the electricity. Now, what's the difference between electrolytes and non-electrolytes? It's actually incredibly simple. Electrolytes form ions. If you have an ionic compound, or a compound that can dissociate to form ions, that will conduct electricity. That is an electrolyte. Simple bottom line. If you have a compound that, in this case, this is sugar, glucose, it dissolves in water because it has all these OH bonds, very polar, but it does not form ions. It is a non-electrolyte. Any questions? Ions, electrolyte, no ions, non-electrolyte. If you had a bathtub full of absolutely pure water with nothing at all in it, yes, you could take your curling iron in there and not worry about frying. If, however, you use like Chicago water that has who knows what dissolved in it, you're fried. Don't try it. All right, we can do reactions in solution. We've seen this. We've done them, actually. We've done them. We've taken solutions of this and that, mixed them together, we got precipitates and stuff like that. We know we can do reactions in solution. But in order to do quantitative reactions in solution, we have to be able to know the concentration of our substances in our solution. That is the concept of molarity. Molarity, very simple, is the number of moles divided by the liters of solution. Very, very simple concept. Number of moles divided by liters, has to be liters, of solution. This is a volumetric flask. They are marked with a little etch mark to show an exact volume. This is a mole. We could say we had 1 mole per liter here. Number of moles and number of liters. It really is that simple. Our abbreviation for molarity is going to be an uppercase M. Now, just to be cruel, chemistry also has something called molality, which you might see in general chemistry. And the abbreviation there is a lowercase m. And they're different. So, when you write molarity, please remember it's an uppercase M. All right, molarity, like we said, is numbers of moles of solute, that's the stuff in there, divided by our volume in liters. If I wanted to make a solution and know its molarity, all I need to know is the number of moles and the volume. Well, here's our 1 liter volumetric. Again, there's a little tiny etch mark around here for exactly 1 liter. What we would do is start off with the volumetric flask, and we would add solid to it, or liquid. We would add a given known amount. So we weigh this out so we know how many moles we're starting with. So we do that. Now we take and we add liquid to it, water, and we're going to add water right up to our 1 liter mark. And when we do this, we now have a solution where we know the number of moles and we know the volume in liters. Any questions? Simple concept here. I am taking 3.25 grams of sodium bromide. I have 1,250 milliliters of solution. What is my molarity? What we need to know is the number of moles of sodium bromide we have and the number of liters of total solution that we have. Now, remember the thing that we say before we go to sleep. Mass over molar mass is moles, right? Here's our mass, 3.25 grams. Here's our molar mass, 102. Mass over molar mass gives us moles. So that's the number of moles that we have. How many liters do we have? Well, this is given in milliliters. Remember, there are 1,000 milliliters per liter. So we need to divide this by 1,000. And that's 1.25 liters. So we know the number of moles, we know the number of liters, we know the molarity. If we look at this, grams are going to cancel. Here we have per mole in the denominator. Remember, the reciprocal of a reciprocal is the thing, so this is going to come up, and it's going to be mole up top here. So we'll have the way you would do this on your calculator. Always want to know that. 3.25 divided by 102 divided by 1.25. And you should get 0.0253 moles from our numerator, liters from the denominator. Now we can show that using molar, because remember our uppercase M simply tells us moles per liter. Sometimes you will see this in textbooks, abbreviated as an italic. Sometimes you will see it with a line underneath it. Again, to point out that this is molar, not just an M. And sometimes some guys use a fancy script M to indicate it. Depending on which textbook you look at, you can see any of these guys. Any are fine. Writing italic is difficult. So just uppercase M is what we're looking for. Any questions? Number of moles, number of liters, molarity. This problem looks a whole lot like our last one. Why don't you set it up? We have 6.47 grams of sodium acetate. Here's its molar mass, and here's our volume. Go ahead and set it up. First of all, we need to figure out how many moles we have. Then we need to convert our milliliters to liters. The number of moles is simply going to be mass over molar mass. The number of liters, we're going to take our milliliters divided by 1,000. On your handy-dandy calculator, 6.47 divided by 82 divided by 1.45 should give you, here we go, 0.0544 moles per liter. Now sometimes you'll see this written out this way. It means the same thing. Remember, we put a -1 sign that simply means per. So this is moles per liter, just like moles per liter here. And of course, both of these simply mean molarity. 0.0544 molar solution. Any questions? Well, this is exactly the same problem. It's just worded differently, isn't it? Here we have, what is this? Potassium, hydrogen, phosphate. We have 238 grams and 275 mils. What is the molarity? Step 1, how many moles? Step 2, how many liters? Set it up. Our number of moles, we have a mass and a molar mass. That gives us moles. We have 275 milliliters divided by 1,000. That's 0.275 liters. Our grams cancel. Per mole goes up. And we get roughly 5 moles per liter. We would say the solution is 4.97 molar. Simple concept, simple calculation. Number of moles, number of liters. Now, of course, there's a tutorial. There are actually 2. This one is called Molarity 1. And it's a table. Everybody likes these. In this, we are given moles, we are given volume, or we are given molarity. And we simply have to calculate what's missing. We remember that molarity is simply moles divided by volume. So you can't get much simpler. Moles divided by our volume in liters. 4.54 is our answer. Here we're missing our volume. So we have to take our basic equation. Remember, our basic equation is going to be molarity is moles divided by volume. And we have to solve for volume. So volume is going to be moles divided by molarity. Number of moles divided by moles per liter will give us liters. Moles divided by molarity gives us liters. So we simply take 0.655 divided by 0.154. Yeah. And this is 4.26. Any questions? One more. Here we're missing moles. Go ahead and figure out how to set it up. Remember, molarity is moles divided by liters. Figure out what moles is and do your quick calculation. I once lectured for an hour carrying somebody else's baby. Really. All right, so moles is going to be given by molarity multiplied by volume. Number of moles, 0.1, or this is molarity, 1.25. This is our volume, 2.92. Multiply them together. 0.365 moles. Nice, simple tutorial. Everybody's going to love it, right? Right. Now we can mess these problems up just a little bit. Let's go ahead and look at some variations on this. This is actually kind of like a real life sort of thing. You go to lab and you have a solution of 0.18 molar KCl. You're going to do a reaction where you need 0.01 moles of KCl. How much of this stuff do you need to add? So what we have to do here is simply solve for volume. Right? It's a word problem, but still, it's not simple. In order to solve for volume, we have to divide moles by mole per liter. Here we have number of moles we want, 0.01. Our moles per liter are 0.18. The problem looks something like this. Moles is going to be, or molarity. This is our definition. So we're going to move our liter up, move this guy down, 0.01, 0.18. Moles cancel, liter comes up, and we get 0.056 liters. If you were asked to give this in milliliters, you would simply take liters and multiply it by 1,000. Sometimes in the tutorials they will ask you for volumes in milliliters or liters or even something strange. But figure it out in liters and then simply do your conversion. All right, well, this is kind of a cute thing. Sucrose, this is table sugar. C12H22O11. We have a 2 molar solution. We have 300 mils of it. How many molecules of sucrose are in there? Now, how in the world are we going to figure that out? How many molecules? Well, very simply, if we know how many moles are in there, we know how many molecules there are in a mole. Thank you, Avogadro, right? All we have to do is figure out moles of sucrose and then calculate, use Avogadro's number to calculate number of molecules. So here we are given a concentration and a volume. You know how you go to bed and you say mass over molar mass, blah, blah, blah? Here's another one. Concentration times volume is moles. Both of those are extremely useful things to remember. Mass over molar mass is moles. Concentration, that's molarity, times volume is moles. Here we have a concentration, here we have a volume. We know how many moles we have. Concentration times volume. I changed this from milliliters to liters. The liters will cancel, and we're left just with moles. This is how many moles we have. Now, how many things are in 1 mole? 6.02 times 10 to the 23rd, right? So we'll take this as our given. Our ratio will be 6.02 times 10 to the 23rd things per mole. Right here. And we simply multiply them together. Our moles will cancel, and we're just left with molecules. In our 300 mils, we have 2.26 times 10 to the 23rd sucrose molecules. Any questions? Kind of a cute way to look at this, I think. Sodium sulfate. We have 2.5 molar sodium sulfate. This is interesting. How many moles of sulfate do we have in 150 mils? And how many moles of sodium ion do we have in that 150 mils? Well, if you think about it, we have a concentration and a volume, so we know how many moles, right? I told you it was important. We have concentration, we have a volume, we know how many moles. Further, if you look at sodium sulfate, how many sulfates are there in 1 mole of sodium sulfate? Just 1. How many sodiums in 1 mole? 2. Now remember, I showed you this cute little movie. Here we have potassium sulfate, same thing. We put it in our beaker. Remember, it breaks apart. If we had 1 mole of potassium sulfate, we would have 1 mole of sulfate and 2 moles of potassium. The ions totally dissociate. So what you do is just look at the mole ratio of your compound. So, concentration times volume. And go from here. So, this is our concentration, mole per liter. This is our liters, 150 milliliters. Total number of moles of sodium sulfate is 0.38. Now, if we have 0.38 moles of sodium sulfate, the mole ratio of sulfate to sodium sulfate is 1:1. 1 sulfate for every sodium sulfate. So, how many moles of sulfate? 0.38. Now the mole ratio for sodium is different. There are 2 sodiums in every sodium sulfate. So we take our 0.38, multiply it by 2, and we get 0.76 moles of sodium. Simply look at your compound, do your mole ratio, and that way you can convert number of moles into the number of moles for each of the ions. So let's do one more of these. Barium chlorate. Remember, chlorate is ClO3 minus 1. Barium is a +2 ion, so there are 2 chlorates here. We have 248 grams and 468 mils. What's the molarity of the solution? Well, that's simple. We have mass, we have a molar mass, so we can get moles. We have a volume, we can get liters. Mass over molar mass gives us moles. Divide that by our number of liters, 0.468, and this is the molarity. .74 moles per liter, or 1.74 molar. Now, what if I asked you, if we had a liter of this, how many moles of barium and how many moles of chlorate? Well, remember, barium is a +2, chlorate's a -1. +2, -1. So we have 2 chlorates for every barium. So for barium, 1 mole per 1 mole. Chlorate, 2 for 1. Simply multiply 174 times 2. That's 174 for barium and 348 for chlorate. We already know everything about this problem. Let's just massage it one more time. We have a 1.74 molar solution of the stuff. If we wanted 0.01 moles, what volume would we need? We have moles per liter. We have moles. How do we calculate volume? Molarity is moles divided by liters. So liters is moles divided by molarity. Divide moles by molarity. Moles divided by molarity gives us liters of solution. And we would want roughly 57 milliliters. Now this last set of problems that we did are basic molarity problems, but they're kind of mixed up a little bit, right? They're word problems, they're mixed up. It only makes sense to write a tutorial where everything's mixed up a little bit. So these are word problems. Same basic concept, except more of a pain in the butt, perhaps, because sometimes you have to express these in funny units or whatever. But what volume in mils, not liters, milliliters, of a 0.055 mole of solution of methanol if you wanted 0.037 moles? Same thing. All we're trying to do is figure out moles, or I'm sorry, figure out volume. We already know volume is moles divided by molarity. So to set the problem up, moles divided by molarity is liters. Right? Here's our number of moles, here's our molarity, 0.066 liters. Only thing is, if you type 0.666 in, it doesn't work because the problem asks for milliliters. So we simply multiply this by 1,000, 666 milliliters. Same problems, just in word format. Let's do one more here. How many milligrams, what a pain in the butt that is, are there in 0.722 liters of a 1.13 molar solution of methanol? And here's its molar mass. So what we're looking for here is mass, right? But we can't simply get mass. We're going to have to get moles first. Once we know moles, we can calculate mass, and then convert it to milligrams. All right, so we have a concentration and a volume. What does that give us? Moles. Concentration times volume gives us moles. We have 0.87 moles of this stuff. Now, we know its molar mass, 32 grams per mole. We know the number of moles. Number of moles times this molar mass gives us our mass, 27.9 grams. It's all the same calculations, isn't it? Over and over again. They look different, but they're the same. Now we have grams, simply convert it to milligrams, multiply by 1,000, and we get 27,900. Any questions? All right, let's look at a couple simple test questions. Molarity of a solution that contains 10 grams of sodium hydroxide and 500 mils is what? Standard test question, nice even units. We're looking for molarity. That's moles divided by liters, right? How many moles? Well, we have a mass and a molar mass. That gives us moles. Mass divided by molar mass is moles. Simply divide that by our volume, and we got it. Molarity is going to be the number of moles of sodium hydroxide divided by our volume in liters. Moles of sodium hydroxide is simply mass over molar mass. Grams will cancel, moles will come up top. And our molarity, it's about half molar. How much calcium nitrate do we need to make 500 mils of a 1 molar solution? Well, you could say if we had 164 grams in 1 liter, we would have a 1 molar solution. And then you could just talk yourself back and forth from that. Another way, we can take our concentration here, 1 mole per liter, and our volume, and get the number of moles that we need. That's our volume, there's our concentration, we need 0.5 moles. We know the stuff weighs 164, we need half a mole. Simply multiply these out, moles cancel, we get 82 grams. Any questions? This next one was a simple show your work. We have a 0.375 molar solution. We have 4.75 liters. How many moles is that? After we finish saying mass over molar mass, what do we say? Concentration times volume is moles. Concentration times volume is moles. The math is very simple. Concentration times volume. Simply multiply them out. 1.78 moles. One more of the test questions. We have 200 mils of sodium chloride. We evaporate it down. All the water's gone. We get roughly 1.5 grams of solid sodium chloride. What was our molarity? Well, that's a really fancy way of saying we had 1.56 grams of this stuff in 200 mils, right? We know a mass, we know a molar mass, so we know how many moles that is. Number of moles divided by our volume, and we get molarity. Our molarity is going to be moles of sodium chloride divided by our 0.2 liters. The moles of sodium chloride are simply our mass divided by its molar mass. On your calculator, 1.56 divided by 58 divided by 0.2 gives you about 0.133. Any questions? So yes, you will see molarity questions on the exam in various forms. Make sure you practice on the tutorials. All right. The last topic in this chapter is simply called dilutions. If we start off with a solution, and let's pretend this was a liter, and we took 10 mils out of here, and we put it into a container with 990 mils of water, we'd have 1 liter again, wouldn't we? We would have 1/10 of the number of moles, or 1/100th, that we transferred. If we took a sample, put it in here, we would again cut it by 1/100th. Again and again. This is the principle of homeopathic drugs, okay? In a homeopathic drug, you start off with a solution with something in it, and you'll dilute it 10 times or so this way. So you wind up with nothing at all in there except water. We'll see that in a minute. And then you pay 20 bucks for it. Don't do that. All right, let's do the calculations here. The thing to remember here is if we dilute a solution, so we have a 1 molar solution, and we dilute it by some factor, tenfold, the volume's going to change, but the number of moles doesn't. The volume changes, but the number of moles does not. We're going to use concentration times volume to figure out the number of moles. And then our new volume to figure out molarity. Concentration times volume gives us moles. Very important. We're going to formalize this in terms of an initial and a final state because we are diluting. We will have an initial volume, an initial concentration, and a final volume and a final concentration. But since the number of moles is the same, this really is an equality. Volume times concentration is moles. This is also moles, and that does not change. So let's see how we do this. We have 0.53 molar sodium chloride. We take 500 mils and dilute it to a final volume of 1750. What's the final concentration of our sodium chloride? The number of moles hasn't changed. Just the volume and, of course, the concentration. Moles have not changed. For our initial state, we will calculate the moles by volume and molarity. For our final state, we want to know molarity, so we're looking here for the final concentration. We know our final volume here is 1750. Our initial volume is 500, and our initial concentration is 0.53. 0.5, 0.53, 1.75, and this is our unknown. Now, all we have to do to solve for C2, multiply these two together, divide by 1.75, something like that. When we do that, liters are going to cancel. That's going to leave us only with moles, or molarity. 0.5 times 0.53 divided by 1.75. Our final concentration, 0.15 molar. Just remember, the number of moles doesn't change. Because of that, volume times concentration must equal volume times concentration initially and in the final state. What volume of 2.1 molar do we need to make 1600 mils of 1.1 molar? So here we're missing V1, aren't we? That's our initial thing. We're missing V1. We know everything else. We know C1, we know V2, we know C2. Concentration times volume is going to give us moles. Simply going to solve for V1. There's our equation. Solve this for V1. V1 is going to be C2 V2 divided by C1, right? (1.1), that's C2. 1.6, that's V2. And our initial concentration is 2.1. All we have to do, 1.1 times 1.6 divided by 2.1, 0.84 liters, or 840 milliliters. All dilution problems are going to come down to this one simple equation. Concentration, volume, moles. All right. Let's look at this a little more closely. I'm going to say we're starting off with 0.53 molar. I'm going to take 10 mils, add it to 990, make a liter. Calculate our new concentration. I'll take 10 mils of that, calculate a new one, and a new one. Our real question is, when we hit the end here, what's our concentration? Okay, we can do this. For our first step, number of moles, well, okay. The number of moles is going to change because we're taking a certain number of moles here and we're diluting it by a factor of 100, right? So we're going to take volume times concentration for each step. In our first step, this is our 10 mils. We have 0.53 moles per liter. We have 5.3 times 10 to the minus 3 moles. That's what we've transferred. In our new liter, therefore we are 5.3 times 10 to the minus 3 moles in this 1 liter. That's our new concentration. Now we're going to take 10 mils of this stuff. That's our new concentration. And we're going to dump it into here. Again, 10 mils. We're now 5.3 times 10 to the minus 3, 100-fold less. Liters cancel. And we're going to drop this by another factor of 100. We're at 10 to the minus 5. That's this guy. The next one, we're going to substitute in 10 to the minus 5 here. Okay? 0.01 times this, cut it by 100, we get 10 to the minus 7. And finally, for our last solution, our starting concentration is 10 to the minus 7, cut it by 100, this is 10 to the minus 9. So that's our concentration at the end. After 4 simple dilutions, we've gone from roughly half molar to 10 to the minus 9 molar. Now this is useful if you want to do things in the lab with real dilute solutions. If I ask you to weigh out 5 times 10 to the minus 9 moles of something, you could never do it, could you? I mean, that's a microgram? You couldn't do that. So you take a solution and you dilute it 2 and 3 times. Calculate it this way and you can get it. Now a fun thing to do at this point is to say, how many molecules of sodium chloride do we have in this solution? In this case, I just asked sodium ions. If we had a 10 to the minus 9 molar solution, how many sodiums do we have? Again, Avogadro told us if this was 1 molar, that would be 6.02 times 10 to the 23rd, right? So we simply want to take our concentration, our number of moles here. Going to take Avogadro's number, moles cancel, multiply it out. We're still at 10 to the 15th sodium ions. Now I told you that most homeopathic solutions are diluted at least 10 of these cascades, right? If we did 7 more of these cascades, just 7 more, how many sodium ions do you think we'd have? 32. We can cut this solution down after 7 more dilutions so that there are 32 sodium ions in our liter. Isn't that astounding? And you still pay 20 bucks for it. Any questions? Well, there is a dilution tutorial. We're looking for our final volume. 140 mils, that's our initial volume. 2.3 molar, that's our initial concentration. 0.56 molar, that's our final concentration. Remember, V1 C1 equals V2 C2. Got it? We're solving here for V2, M1, V1 over M2, 0.058 liters. Problem asks for it in milliliters. Simply multiply by 1,000, and we're at 580. Slightly different. 440 mils, 0.051 molar. This is V1, C1. Our volume here is 0.88 liters. That's V2. We're simply solving for C2. See how simple these are? C2, concentration, is our initial molarity times our initial volume divided by our final volume. There's our numbers, 0.026 molar. Let's look at one more here. Go ahead and pick out the points here. Pick out your V1, C1s, and stuff like that. We're looking for liters here, right? We have 640 mils, 0.6 liters, that's V1. 2.8 molar, that's our initial concentration, C1. Our final concentration is 0.9, so we're simply looking here for V2. V1, C1, V2, C2. Look at the problem, pick out the points. V2 here, our initial molarity times the initial volume divided by M2, 2 liters. Let's see. Okay. I forgot to say this. Let's back up just a touch. So we need a total here of 2 liters, right? So this one is tricky. But we've already got 640 mils, right? We need a total of 2 liters. So we have to get how much we have to add. We have to subtract these 2. Our 2 liters minus our 0.64 liters, we need to add 1.4 liters. So if you get one of these in your set, it's a little more complicated. Remember, you're looking for how much you have to add to it. All right. These are the tutorials for the previous chapter. These are the 3 for today. Molarity 1, Molarity 2, and dilutions. Please make sure you do them all. The more you practice, the better off you'll be. Any questions?
Do you mind going back just a little bit?
Of course I do.
I just wanted to see the rest of the calculation for the dilution or the last one.
Dilution before the last one. Let's see. Maybe it's simpler to do it this way.